Hello, everyone, and welcome to The Explainer. Today, we're taking an absolutely epic time travel journey. We're going to rewind the clock all the way back to the very beginning to explain how Earth was made in a simple way. We'll be looking at exactly how our planet transformed from a molten, chaotic hellscape into the lush, breathable paradise we live in today. I am so pumped to walk you through this incredible chronological story.
Okay, let's dive into this. Imagine stepping out of a time machine onto Earth roughly 4.5 billion years ago. If you were looking around for a nice blue sky, or maybe some water, or literally even solid ground under your feet, well, you'd be severely out of luck. Instead, you'd just be staring at this global ocean of liquid rock hitting temperatures of 2,000 degrees Celsius. No way you'd survive that. And if you somehow tried to take a breath, the sheer amount of toxic carbon dioxide and sulfur in the atmosphere would literally kill you in seconds. The contrast between that lethal environment and the living, breathing sanctuary we're sitting in right now is absolutely shocking. So how on earth did we get from that to this?
That brings us to Section 1, Birth in the Solar Nebula. To really wrap our heads around this, we have to go way, way back. Before there were rocks, before magma, heck, before our sun even had planets. 4.6 billion years ago, our story kicks off in the solar nebula. Back then, this was just a massive, dark cloud of interstellar gas and dust. Basically, the dead leftover stardust from previous cosmic eras. So what kickstarted the whole shebang? A nearby supernova. A massive shockwave from that exploding star slammed into our dark cloud, causing it to collapse under its own gravity. It started to spin, eventually creating a massive disk around our newborn sun. Now, right in the inner solar system, where our future Earth was hanging out, it was way too hot for gas or ice to condense, so we were left with these microscopic specks of rock and metal. As these tiny specks rubbed together in the spinning disk, something very familiar happened: static electricity. It caused these microscopic specks to cling together, behaving literally exactly like the dust bunnies gathering under your bed right now. Over millions of years, this simple process of accretion meant those little dust bunnies grew into pebbles, then boulders, and eventually planet-sized building blocks. Gravity finally took the wheel, slamming all these rocks together until Earth emerged as this glowing, chaotic protoplanet. Which leads us right into Section 2, the moon-forming collision. And this brilliantly illustrates what happened next. You see, our newly formed molten Earth was absolutely not safe yet. Just as things were kind of starting to settle down, a rogue Mars-sized protoplanet that scientists call Theia was on a direct collision course with us. Theia grazed Earth at a mind-bending 25,000 miles per hour. The energy of this impact was just catastrophic. It completely vaporized Theia and practically stripped away Earth's entire outer crust. Both the crust and the vaporized protoplanet turned into this massive ring of superheated debris orbiting the Earth. Finally, over a matter of decades, which is an absolute blink of an eye in cosmic time, gravity caused that debris to clump together to form our moon. But here's the really crazy part about that collision. It permanently altered our planet by knocking it right off its axis, giving Earth a 23.5-degree tilt. And that exact tilt is the fundamental reason we experience seasons today. Seriously, every single summer and winter you've ever lived through is the direct legacy of a planetary collision that happened 4.5 billion years ago. How wild is that? Let's keep moving forward. Section 3, Cooling and the First Oceans. With the moon now orbiting our newly tilted Earth, we transition into a pretty brutal era where the fundamental building blocks of our modern surface began to take shape. It's called the Hadean Eon. Named after Hades, the Greek god of the underworld, Earth was basically a glowing ball of magma for tens of millions of years. But during this time, a really crucial sorting process was happening. Heavy elements, primarily iron and nickel, sank straight down to the center of the planet. This formed our dense metallic core. Meanwhile, the lighter silicate rocks naturally floated to the top. As the planet gradually cooled, those lighter rocks slowly began to freeze into a thin rock crust right over the magma ocean. But you might be wondering, how did a hot, dry rock get covered in so much water? Well, first, thousands of volcanic vents in that newly formed thin crust began spewing out massive amounts of water vapor, carbon dioxide, and nitrogen. Then, Earth endured what we call the Late Heavy Bombardment. This was a staggering 300-million-year meteor barrage where icy comets and asteroids just endlessly hammered the planet, delivering vast quantities of extraterrestrial water. Finally, the planet's crust cooled below 100 degrees Celsius, and this was the tipping point. The atmospheric water vapor condensed into clouds, triggering a truly epic torrential rainstorm. And guys, this wasn't just a bad weekend of weather. This rainstorm lasted for thousands of years, eventually filling the massive basins to create Earth's very first liquid oceans. That takes us to Section 4, the Great Oxidation Event. Now, what's really interesting about this slide is the sheer visual difference. By 3.8 billion years ago, Earth officially had oceans, but it looked entirely alien. The water was incredibly rich in dissolved iron, which actually turned the oceans a murky green. And the atmosphere, a toxic pinkish-orange haze of methane and CO2. Yet, if we fast forward to 2.4 billion years ago, we see rusted blue oceans and a clear, oxygen-rich sky. It's like two completely different planets. So how did we get this incredible transformation? Well, the answer actually lies in the dark waters of those early green oceans. The whole transformation was entirely thanks to cyanobacteria. These simple, single-celled microbes were literally the ultimate microscopic heroes of our planet's history. They evolved around 2.4 billion years ago and effectively invented photosynthesis. So they used sunlight to break down water for energy, but in doing so they released what was to them a toxic waste product. Oxygen. This triggered the Great Oxidation Event. The oxygen pumped out by these tiny microbes literally rusted the dissolved iron right out of the oceans, turning them blue. The leftover oxygen flooded the atmosphere, turning the sky blue and forming an ozone layer that blocked lethal cosmic radiation. Life had fundamentally engineered the planet's atmosphere, a real game changer. Let's move to and see how this builds. Section 5, a living, dynamic machine. You see, Earth didn't just form once billions of years ago and stop. It is constantly engineering itself, and that ancient geologic history ties directly into your survival today. Remember that heavy iron that sank to the core during the Hadean Eon? Today, that liquid iron is still spinning deep underground, generating a powerful magnetic shield that protects our modern electrical grids and our very bodies from deadly solar flares. And that early crust we talked about? It fractured into plate tectonics. Those plates are constantly shifting and recycling carbon to regulate our global temperature. These chaotic planetary mechanics are exactly why Earth remains completely habitable for us right now. This brings us to a really powerful summary of our entire journey today. Out of cosmic chaos, gravity, collisions, and microscopic life, engineered the only known sanctuary for life in the universe. It is just an incredible underdog survival story. From a literal dust bunny in a solar nebula, through a planetary collision, a meteor bombardment, and toxic green oceans, Earth completely defied the odds to become our modern paradise. And that wraps up our explainer on how Earth was made. But considering that Earth is still this massive, active living machine right beneath our feet today, what do you think our planet's next major evolution will look like millions of years from now? Let me know. Drop your thoughts in the comments below. Also, tell us what complex topic we should break down and explore in our next explainer. Keep learning, keep asking those big questions.